No, I mean,
We want to do that.
Bonsoir tout le monde et bienvenue au Centre des sciences de l'Ontario. C'est un vrai plaisir vous souhaiter une chaleureuse bienvenue ici aujourd'hui et vous reçoit ce soir pour la 10e soirée de notre série de grandes conversations scientifiques. Good evening and welcome everyone. My name is Maurice Bitran. I am the CEO and Chief Science Officer of the Ontario Science Centre. And it's a real pleasure to welcome you today to the second event of our four speaking series, Great Conversations, started this year. Before we begin, I'd like to take a moment to recognize that Toronto is located in the traditional territory of Indigenous people dating back countless generations. And I would like to show my respect for their contributions and recognize the role of treaty making in what is now Ontario. Hundreds of years after these first treaties were signed, they're still relevant today. Great Conversations offers a forum for discussion, debate, and discovery. In bringing leading global experts to share their ideas with our community, we aim to start conversations about important topics in the nexus of science and society. The question, are we alone in the universe? Resonates through the ages, from prehistory to our days, as a defining cri de coeur of our species. Few people in the world have done more to search for answers to this profoundly human question than tonight's speaker, Dr. Jill Tarter. As a pioneer in the search for extraterrestrial intelligence, or SETI, Dr. Tarter has put the increasingly sophisticated tools of radio astronomy, that branch of astronomy pioneered in the 1930s by the American physicist and radio engineer Carl Jansky, which you saw Jansky's radio telescope here in the slides before, to detect that elusive needle in an incredibly vast cosmic haystack. Co-founder of the SETI Institute, Jill is one of the most influential scientists in extraterrestrial intelligence research. There are few aspects of this fascinating field that have not been touched by her work spanning over 40 years. You may have seen part of her story if you saw the movie Contact, based on the Carl Sagan novel, in which the protagonist, who is played by Jodie Foster, is partly based on Jill. Tonight, we will be treated to Jill's perspective on what searching for extraterrestrial intelligence has meant for our species. Jill's presentation will be followed by a one-on-one conversation with our moderator, Ivan Seminac, science reporter for Canada's national newspaper, The Globe and Mail. And then you will have your chance to ask your questions. I would like to acknowledge that Dr. Tarter is here this evening as part of the Charles Darrow Lecture Series, presented in collaboration with the Royal Astronomical Society of Canada, Toronto Centre. The Ontario Science Centre has an over 20-year-strong relationship with the Royal Astronomical Society of Canada. Together, we provide astronomy, programming, and events, such as monthly solar observations and star parties in the Greater Toronto area, thus allowing the community to explore the wonders of the universe without leaving the city. During the solar eclipse last month, the Royal Astronomical Society of Canada helped us to celebrate this event, and we had, I think, 3,000 pairs of eclipse glasses to give out. Over 10,000 people showed up. We were totally overwhelmed. And it was a wonderful experience, and the volunteers of the Royal Society of Canada, Astronomical Society of Canada, were here side by side with our hosts, helping this huge crowd look at this wonderful event. Tonight's event is another example of our continued collaboration, which aims to engage and educate the public in space sciences. And now I would like to invite Dr. Ralph Chu, President of the Royal Astronomical Society of Canada, Toronto Centre, to say a few words. In addition to serving as president of RAS, Dr. Chu was a professor at Waterloo School of Optometry, Optometry and Vision Science for 30 years before retiring in 2012. Dr. Chu and I go back a long time. We were just remembering that we served in CSA committees on sunglasses a long time ago, and also work on issues of ultraviolet exposure of workers. And it's a great pleasure, Ralph, to welcome back here to the podium as the president of the Royal Astronomical Society. Toronto chapter.
Thank you, Maurice. It is nice to be back here. Some of you may not know this, but back in 1970 to 73, I actually was a staff member here at the Science Center, and I actually set up the first astronomy programs that were offered here during that time, including for the 1972 solar eclipse. So I've got a very long and happy history with this place, and it's great to be here. My role tonight is to talk a little bit about the Charles Darrow Lecture Series, of which Dr. Tarter's talk tonight is the first one. The Charles Darrow Lecture Series was initiated by Professor Sarah Seeger to honor Charles, who is her husband, for his service to the RASC Toronto Centre and for his passion and enthusiasm for astronomy. Together, Sarah and Charles set up the lecture series to thank the Toronto Centre of the RASC and its volunteers for their outstanding public outreach contributions and for opening the world of astronomy to many people, including Sarah during her childhood. Professor Seeger is an exoplanet astrophysicist at the Massachusetts Institute of Technology, and she is both an honorary lifetime member of the RASC National Organization and, with her family, a Toronto Centre member. Charles and Sarah actually met through the RASC a few years ago, and since that time, Charles had met many of the famous astronomers we are all inspired by. The goal of the series is to bring some of these people here to Toronto Centre for you to hear from them directly, and it really is a great pleasure to welcome Dr. Tarter as the inaugural lecturer for that series. And now to introduce our speaker this evening, I'll call on Paul Delaney, who is a professor at the York University Department of Physics and Astronomy, and our second vice president for programs. Paul?
Thank you very much, Ralph. Good evening to everybody. I'm glad there's such a great audience here for this terrific event this evening. The fact that I'm here to introduce our speaker, it seems a touch redundant because you wouldn't be here if you did not already know a great deal about her, but nonetheless I was asked to do it, so I will do it. Jill Tarter, she picked up her engineering degree, her bachelor's degree from Cornell University, just across the lake, but then she decided to head west to warmer climes, and she picked up her master's and her PhD at UC Berkeley, the University of California, Berkeley campus. It was while she was working as a graduate student that the SETI bug sort of took a piece out of her, and she started doing the exploration in this field that has literally led to a lifelong passion now spanning close enough to 40 years. I would also challenge you, just for a moment, no Googling. She was a part of a project from NASA called Serendip, all the way back in her graduate student days. Now, as I said, no Googling. For the first two letters, S and E, search for extraterrestrial. The rest you're going to have to figure out, and if not, you can ask her afterwards. She has spent 40 years researching SETI. In fact, the term SETI and Jill Tarter are truly interchangeable. As Maurice indicated, the primary star in the Contact movie, the book was Carl Sagan, the movie featured a woman scientist by the name of Ellie, Jodie Foster, and it was in very large measure crafted on Jill's life. So go home, dig out your DVD, dust off your VHS recording. That's my case. I strongly recommend, after you've heard tonight's presentation, go back and sort of connect the dots. At any rate, as I said, it is my great pleasure to introduce the person who really is associated with SETI, the search for extraterrestrial intelligence. She is the Bernard Oliver Chair at the SETI Institute. She stepped down as its director in 2012. Jill Tarter.
Oh, so thank you. Thank you to the Ontario Science Centre and the RASC and to Charles Darrow and Sarah Seeger for making possible my appearance tonight. And it's a pleasure to be here in Toronto. Thank you for the California weather that I've been enjoying. And I'd like to spend some time tonight talking about a different way of thinking and experiencing the universe, a perspective that astronomers naturally gravitate towards, and that's a cosmic perspective. And I think that I can convince you by the end of my presentation that it's a very important perspective, one that you should all take to heart. So when we begin to talk about life in the universe and we begin to think about life here on this planet, we need to understand that our story, the story of humans, right, begins billions of years ago. Humans measure their history and their lineage not just back through the centuries of our families, not just back through the millennia of human civilizations with its buildings, its art, and its many forms of government, not just back over the millions of years since we branched off from the great apes, not just back the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen thanks to the photosynthetic labors of cyanobacteria, not just back to the formation of the sun and our solar system 4.6 billion years ago, but back another 4 or 5 million years beyond that to a giant molecular cloud that was contaminated by the winds of Wolf-Rayet stars and the debris of supernova explosions. The iron molecules in the hemoglobin, molecules in your blood, the calcium in your bones were fused inside the core of massive star that blew up, exploded billions of years ago and left behind debris similar to this modern supernova explosion. And that's what you and I are made of. Literally, we are made of star stuff. And it takes a cosmos to make a human. And it's taken us millennia to piece together the story that tells about our history. And today we continue on a journey of discovery because we're curious about who we are and why we are and what else there might be, and of course, who else there might be. And as we go along this journey, we're forced to think in a different way about what we mean by here and now. Right? So here, well, okay, right? We're undoubtedly in the Imperial Oil Auditorium here at the Ontario Science Centre, right? In Toronto, seen here in this view from Google Earth, a view we're becoming more and more familiar with. And if you were at the altitude of low Earth orbiting satellites, you'd see us here. And since 1968, when Bill Anders on Apollo 8 took this image of the Earthrise as he came around the limb of the moon, we've been able to see our planet as a whole floating in the darkness of space. That was our first real cosmic perspective. A few years ago, we took a selfie. Cassini turned around, looked back, and saw us all here on the little dot that's up there. Really, that's all of us. I hope you got the memo, put on your clothes, and went outside and waved when this photo was taken. We did try and get people involved. And before that, in 1990, as the Voyager 1 spacecraft was passing Neptune, it turned around and it imaged this pale blue dot here. This is our home, and we are here at the outskirts of a spiral galaxy. We're not near the center, we're in the boondocks, and no, nobody took a picture, right? This is another galaxy that we think looks like the Milky Way, and there are 400 billion other stars in this galaxy, and that galaxy is here, right? And there are over 200 billion other galaxies in the observable universe. And those little smudges, those little dots are not stars. They're galaxies full of hundreds of billions of stars each. And some of these galaxies are smaller and fainter and farther away. And so we're reminded, as we look farther out in space, we indeed, because of the finite speed of light, are looking farther back in time. And so we have to understand what we mean by now, right? From this perspective, we are in the current epoch of the universe's 13.8 billion year continuing evolution, from the Big Bang to big brains and beyond. It's terrible to blow your lines. Big Bang to the big brains and beyond, right? And, we're not yet completely comfortable with this picture, not even the scientists, because we now understand that everything that we have been studying for millennia represents only 4% of the mass energy density of the universe. The other 96% we call dark matter, dark energy. Dark is astronomical code for we don't know. We don't have a clue. We're trying to figure this out. And as we go farther back in history, our observational evidence tracks beautifully this cosmic evolution story that we have manufactured until we get back to the very beginning, and then we are still unable to make gravity and quantum mechanics play nice together. So there are mysteries and unknowns and problems to be solved. But yet this is the most self-consistent origin myth that we have ever constructed. And it will change with time as science unveils new information. So over my career, embarrassingly long, as you already know, there have been two amazing game changers in terms of the questions of life beyond Earth. The first is extremophiles, the second, exoplanets. So extremophiles, forms of life that live in environments when, as a student, I was told couldn't possibly harbor any sort of life. We knew back then, of course, that life had to live within the boiling and freezing points of water, had to be at about 1 atmosphere of pressure, 1 bar, had to be neutral in pH. Of course, we needed sunlight, the energy that drove all life. Well, all that is not right. And over these decades, we have learned about amazing microbes and macroscopic creatures that live in all of these different environments and are perfectly happy there after billions or millions of years of evolution. And we are eager to know whether creatures that are life as we don't yet know it maybe a bit more extreme than the extremophiles that we find on our planet, might be living somewhere else in the solar system. And so today we have rovers on Mars, the Mars Science Laboratory, the Curiosity rover, sending back pictures of this frozen desert world, right, that looks just like the deserts of Southern California. And we are exploring, not precisely for evidence of life, but for the ingredients that we think were necessary for life. Carbon, water, more clement temperatures in the past. And Curiosity has been showing us that, as we once thought, liquid water flowed for significant periods of time on early Mars. Early Mars was indeed wetter and warmer, and you see these rock formations that look very much like the sedimentary rocks or muds that you would see in a river delta. And when Curiosity uses its drill to bore into those rocks, lo and behold, we find carbonates, right? Not necessarily, not life, but carbonates, an important ingredient for life as we know it, and life that we know from the extremophiles on our planet. And not only did water exist on Mars in the past, but it still exists today. When it gets a bit balmy in the summer on Mars, we see these recurrent slope linii, which are in fact water, briny water running downhill in gullies on the surface of Mars. And this actually changes the whole scenario for exploration of this planet, because we're interested to look for evidence of extant or extinct life on Mars. And wouldn't it be a shame if we were to find life and then to realize that it was microbial life that we brought with us because we hadn't sterilized our spacecraft adequately? So there's an international protocol set by an international organization called COSPAR that tells us how clean we have to make our exploration tools, depending on the potential for supporting life. And while we thought that there was no water on the surface of Mars, we could get away with one level of sterilization because anything that we brought with us was very unlikely to be able to survive on the surface. But now we want to go and explore these watery environments. So we got to clean up our act even more as we go forward with our exploration of Mars. And suppose Mars doesn't yield any evidence of past or present life. There's a lot more real estate, bodies out there in the solar system. We're particularly interested in the moons of the giant planets. So Ganymede, Callisto, Europa, giant moons of Jupiter, and Titan, giant moon of Saturn. Now, these moons of Jupiter are ice-covered. Nevertheless, beneath that ice, we're pretty sure that there are large volumes of watery oceans. So Europa is about the size of our moon, and we think that there's twice as much water under the ice there as there is in all of the Earth's oceans. And Titan isn't ice-covered. Titan actually has liquid lakes on its surface. But those lakes are methane and ethane. It's too cold for liquid water. Water is there, but it is ice beneath the surface. And so these are really intriguing worlds that we want to explore in the near future. And there was even a big surprise when Cassini reached Saturn and began exploring. Here's this pipsqueak moon, this tiny little moon called Enceladus. Probably not very interesting. Well, guess what? The south pole of Enceladus has cryovolcanoes. these plumes of frozen water and materials from the oceans that are out underneath the ice cover of Enceladus, and they're being served up. We don't have to figure out how to melt or drill through the ice to sample the oceans beneath to see if there's potentially any life. There's been water there, salty water, for 4 billion years. We think that perhaps life might have started in the oceans of Earth, so it's not unreasonable to question whether life might have started in the oceans of Enceladus. And here it is. It's a free lunch, as free as anything is in the solar system. We don't have to drill. We don't have to melt. We can fly through the plume and sample what's in the ocean. In fact, we've already done that with Cassini, but no one expected Cassini to be able to go look for life, and so the mass spectrometer on Cassini can tell us that in that ice, water ice, there's nitrogen, which would be food for different kinds of life, but it can't tell us about large biomolecules that might be products of life, because it just wasn't built to look for molecules that big. All right. We also think that Europa has similar plumes, although they're not as persistent, not as reliable. Here's another place we want to go explore. Lots to do in the coming decades for exploring our solar system, looking for biomarkers. And what if we don't find any evidence of life beyond Earth in our solar system? Well, what about the other stars? What about planets around other stars? What about exoplanets? When I was a student, we knew of 9 planets. We've since lost one, but we have gained thousands and thousands of exoplanets, right? And that's new and exciting. We now, in fact, can say that there are more planets than stars in our Milky Way galaxy. And they come in many different sizes and varieties, and there are types of planets that we don't have in our own solar system. We call them super Earths or mini Neptunes. And we wonder about life on these worlds. And we have a way of thinking about that. We say, well, you probably need liquid water. That's something we're holding on to. It's anthropocentric, or at least it's what all life on this planet needs. And so we're holding on to that, and we're thinking about what we call the habitable zone of other stars. So a planet that would be not too close and too hot, and not too far and cold from its host star. So if it had an atmosphere, perhaps water could be liquid on the surface. And most of the stars in the sky are not like the sun. They're a lot less massive than the sun. We call them red dwarfs. The majority of stars in our galaxy are these small dwarf stars, which live for a very long time. And we are quite puzzled about whether the environment around those small stars would in fact support life on a planet at the right place. But guess what? The very nearest star to us, a star that's a red dwarf called Proxima Centauri, it has a planet. And it's in the habitable zone. So as our theorists scratch their heads about what would life be like around a red dwarf, is it even possible? Nature's shown us, given us a sandbox, a laboratory in our own backyard to be able to study this question. And exoplanet systems come in all shapes and sizes, and the architectures are amazing. Here's one that even made above the fold on the New York Times. This is another small red dwarf star that has 7 planets that are Earth size around it. And 3 of those are perhaps in this habitable zone. That's such a bizarre system. If you look at this chart, the bottom shows you the inner region of our solar system, and the green area, roughly between Venus and Mars, that's the habitable zone of our solar system. And that star and all 7 planets would fit well inside the orbit of Mercury. Yet it has its own habitable zone, and 3 of the planets lie within. So we're really eager to study this system some more, and particularly my colleagues at the SETI Institute look at these planets, and we look at instances when 2 of the planets in the habitable zone line up, and we observe them then, because suppose there's life on all of these habitable planets, and they're talking to one another. Well, we get to listen in on the conversation. We have a direct line of sight when these planets are in conjunction. So it's a special system for us. And the space agencies of the planet are embarked on planning and building the next series of exploratory missions to planets and moons in our own solar system. And they are going to be looking for biomarkers of microbial life. But if you are interested in the mathematicians as opposed to the microbes, and that's what SETI wants to know, we need to not be looking just for biosignatures within our solar system, biomarkers in our solar system, and biosignatures in the atmospheres of exoplanets. But we need to go looking for technosignatures. We need to be looking for someone else's technology that's modifying their environment in ways that we could detect across the vast distances between the stars. We don't necessarily know what that technology might be for, but a concerted effort of observing at many different frequencies might be able to detect it. And so this story of SETI, this journey, began a little more than 50 years ago using radio telescopes. At the beginning of this century, we began to use optical telescopes, and today we're trying to push our observations into the near infrared so we can see farther than we can in the optical. And what we're looking for is engineered signals. Okay? We're looking for something that doesn't look like noise, that doesn't look like Mother Nature and the standard astrophysical emissions that astronomers are very eager to study. We're looking for artifacts. So I've drawn you a chart here which has frequency on the horizontal axis and time on the vertical axis. And most of that's noise. And you can see that. I don't have to tell you that. Most of that's noise. But there are some artifacts in there. In particular, this is observed at radio frequencies, and it's what the planet Mars looks like to our instrumentation when the Mars Reconnaissance Orbiter or the Mars Express spacecraft are transmitting information back to the Deep Space Network. So we can detect those narrowband radio signals, and they look nothing like nature. So we look in the radio for frequency compression, engineered signals. We look in the optical for time compression, for signals that are like the bright pulses from a huge laser amplified by a large telescope. So bright, short pulses, time compression in the optical, narrowband, frequency compressed signals in the radio. Excuse me. Well, suppose we're looking for the right thing. Whether or not SETI succeeds depends upon the distance between any 2 technological civilizations. And that's not only distance across space. We have to be close enough to be able to be sensitive enough to detect one another, but it's distance across time, right? if technological civilizations don't last for a long time, and that's long in terms of cosmic, not human, timescales, then they're going to pop up and go away, and there'll never be two of them that are co-temporal, that are around at the same time in the 10 billion year history of our galaxy to be able to discover one another. But you can turn that around. And that's what Phil Morrison, co-author of the 1959 first SETI paper in Nature, does when he says that SETI is the archaeology of our future. So, let's assume we make a detection. Because of the finite speed of light, any information in the signal will be telling us about their past. But because we make a detection, we know that technology, on average out there, must be long-lived. And if someone else can make it through the technological sort of adolescence where we find ourselves today, then we can as well. And it tells us that it's possible for us to have a long future. Now that's a message and information that isn't available in any other way that I know of. And so I find it extremely positive to think about what we could learn, even if it's just a cosmic dial tone, a proof of existence. It means that we can figure out a way to have a long future here on Earth. So, we've been doing this sort of thing for more than 50 years, and what have we done? How much have we accomplished? Well, there are 9 different parameters that you have to get just right to detect an electromagnetic signal. Light, radio, infrared, assuming that that's what we should be looking for. And if you take the total volume that could be represented by those 9 different parameters and say, okay, that's what I have to search, and I'm going to set that volume equal to the Earth's oceans. How much searching have I done? The answer is at the lower right-hand corner. It's 1 12-ounce glass out of the Earth's oceans. Not very much. And it's particularly because we've been using tools that have been built for other purposes. But now that computing has given us an enormous amount of capability, we've begun building tools that are actually commensurate with the size of this vast search that we're undertaking. And so our glasses are getting bigger, and we're dipping them in the ocean much, much faster. And in fact, because it's mainly computing, the speed that we are improving is not just a linear speed, but it's exponential, right? It's factors of 2, and then factors of 2 more, and factors of 2 more. And if you've ever listened to the story about 1 grain of rice on the checkerboard, you know that without too many iterations, the whole planet is covered in grains of rice. So exponentials are extraordinarily powerful, and our search is becoming much more powerful. So this is like showing off baby pictures, right? Here's the Allen Telescope Array in Northern California that the SETI Institute has built. It's the first time we've built a large radio telescope out of a large number of small dishes that has many advantages for doing surveys and for being economical. And we hope that in the future, the Allen Telescope Array may be successful in finding these engineered signals that we're looking for. From 2011, when Kepler reported the first exoplanet detections, until last year, we pointed our radio telescopes at places where Kepler told us that there were planets. But then Kepler told us every star has a planet, at least one. So last year we changed our approach, and our current target list is 20,000 closest stars, almost all of which are these small red dwarfs. And so here is a two-dimensional map. It's got strange coordinates, not for the RASC people, but for the other people that aren't astronomers. It's a two-dimensional representation of the sky. And you can see we're beginning to cover in that sky, and you can see one very dense clump of points. Those are the Kepler exoplanets. That's the 100 square degrees of sky that the Kepler spacecraft stared at. And at the declination of the Kepler field, we've in fact ignored targets in favor of Kepler until today. So we've got a stripe there, here, that we're not covering or haven't covered to date. And there's another stripe on this field. And that's the orbit where geosynchronous satellites are circling our planet. And we don't look there because those guys are noisy, right? That's our own technology, and we're really trying to detect someone else's. But the challenge of our field is discriminating between our technology and someone else's potential technology. So this is what we're doing at the SETI Institute, and recently there's been new players in the field. Mr. Yuri Milner has pledged a very large amount of money over the next 10 years to the Berkeley Breakthrough Listen project, and they are renting time on large telescopes and building SETI-specific instrumentation to put at the back ends of those telescopes. So this is the Green Bank Telescope in West Virginia. This is the Parkes Radio Telescope in Australia. This is the automated Planet Finder Telescope at Lick Observatory in California for optical SETI. And there's instrumentation on these three telescopes today. And there have been memorandum of agreements signed with the large telescope in China, FAST, with Meerkat, an array of telescopes looking a bit like the Allen Telescope Array being built in South Africa, and the Jodrell Bank Lovell Telescope in the UK, plus an array of VLBI telescopes called E. Merlin. And instrumentation will be built for those telescopes in the future. And there's actually other SETI ongoing. Some of you may have been using SETI at home as a screensaver on your computers and may have been using it for a decade. It's still running. It's taking data, or it was until Hurricane Maria, taking data from the Arecibo Observatory in Puerto Rico. There's a low-frequency array in the Netherlands and across Europe and the UK that's looking for transient signals at low frequencies. There's a group in Italy, SETI Italia, using a large telescope in Medicina. There's a sky survey being conducted by scientists at the Jet Propulsion Laboratory in Southern California. The Japanese occasionally hold these observing campaigns where radio telescopes and optical telescopes from a number of countries look at the same source at the same time to see if they can find any anomalies. And these are the radio programs on the air today. And then there's optical SETI. Here's a sky survey from the Harvard University that looks at 80% of the sky that passes overhead during the year. There's data from the Keck Observatory in Hawaii, these twin 10-meter telescopes, data that's being collected to detect exoplanets by radial velocity studies. That data can be interrogated looking for engineered signals, either continuous or pulsed laser signals. Here's an amateur optical SETI observatory at Boquete in Panama, and data from the WISE spacecraft, which surveyed the sky at infrared frequencies. That's being looked at to see if we can see strange excess infrared radiation coming from a civilization that's advanced enough to capture all of the sunlight from its star and repurpose it for doing work, or even more advanced civilizations, K3, Kardashev 3, which capture all the energy output of its galaxy to reuse for doing work. And the future allows us to think about what we can do for looking for biosignatures, finding these chemical fingerprints in the atmospheres of exoplanets from large telescopes in the future. Here's the JWST Space Telescope that will launch in 2018. It will be able to do some spectroscopy on the atmospheres of what we call hot Jupiters, massive giant planets right in close to their star. All right, the first planet around a main sequence star, 51 Peg B, is just one of these things. It's something as massive as Jupiter, yet it's so close to its star, its period is not 15 years, it's 4.3 days. Right? These hot Jupiters may give us some clues as to what's in the atmospheres of these planets, although we don't think they're likely to be abodes for any kind of habitable worlds. We'll also be launching space telescopes that have coronagraphs embedded to block out the light from a star so we can maybe image the planets around them. And maybe not only a coronagraph within the telescope, but a star shade that orbits far in front of the telescope to block out the bright star so we can see the faint planets. And then in the very distant future, something that we unromantically call the Large Ultraviolet Optical Infrared Telescope, right? It's just a gleam in our scientists' eyes, but this would be a large enough telescope to really do a good job at imaging planets and doing chemical assays of their atmospheres to look for biosignatures. And for SETI, well, we've got large ground-based optical telescopes coming online, the 30-meter telescope, the European Extremely Large Telescope, the Large Synoptic Survey Telescope, and we hope we can put optical SETI instruments on these. And at the SETI Institute, we just finished an Indiegogo crowdfunding campaign to fund the second stage of prototyping of what we call laser SETI. Ultimately, it'll be 96 small wide-angle cameras around the planet that can look at all the sky all the time and be sensitive to transient sources. The large telescope in China will begin doing SETI. Eventually the square kilometer array, thousands of small telescopes in South Africa will begin doing SETI. And ultimately, perhaps we'll build something that's now called Colossus, something that's big enough that it can capture the waste heat, the inevitable result of the second law of thermodynamics, from converting the energy from some central source like a star into work and radiated heat. And this is kind of the ultimate. If either the second law of thermodynamics doesn't work out there, or there aren't any technologies that are capturing energy and using them in ways that we understand. So we're looking forward to this future of new instrumentation. And the reason I'm telling you about this, the reason I'm hoping that you'll get interested in SETI and actually try and find ways to work with us on this project, is because I think SETI actually does a fantastic service. It actually holds a mirror up to the planet, to all of us, and says, hey, you guys, look, in that mirror, you're all the same when compared to someone else. A discussion about SETI, thinking about SETI, must in fact trivialize the differences among humans that we find so difficult to deal with today. And so I think SETI is enormously important to pursue, to pursue as a global enterprise. And it will do a good deal of benefit. It will give us a huge positive impact, even before it detects a signal. If it helps us to share this cosmic perspective, to figure out a way to work on a project that isn't threatening, that is exciting and intrinsically of interest to humans, because we want to know if anyone else is out there. We want to calibrate our place in the cosmos. And if we can work globally to figure out how to do this project, then that's a really good first step to figuring out how to collaborate globally on all these other challenges that we have. Challenges that do not respect national boundaries. Challenges that are going to require global solutions. And so I leave you with words from Caleb Scharf, astrobiology chairman at Columbia University, and now developing a large astrobiology enterprise in Japan. And Caleb reminds us that on a finite world, look at that picture, that's a finite world, a cosmic perspective isn't a luxury, it's a necessity. Thank you.
Okay. Wonderful. Wasn't that great?
Thank you. Thank you.
Thank you for your words, Jill. I think that SETI exemplifies better than any other human undertaking our need for discovery, our quest for discovery as a species. And I can't think of a better representative of SETI than Jill Tarter. So this is fantastic. And now for the second part of our program, we're going to have Ivan Seminek from the Globe and Mail to sit in conversation here with Jill to ask some questions, and then we have the questions from the audience. Ivan, please. Ivan, well-known scientific reporter from the Globe and Mail, astronomy graduate as well, and alumnus of the Ontario Science Centre as well. So welcome back home, Ivan, and we look forward to the conversation.
Thank you very much. Thank you. And another hand for Dr. Tarter. I just want to thank you for that. Thank you. It's a pleasure to be here and also to be with you, Dr. Tarter. And I'm going to try very hard to avoid what happened the last time I was on this stage with a famous SETI scientist or a famous proponent of SETI. It was a long time ago. I won't say exactly how long ago, but the astronomers in the audience will understand if I say that the light that left Vega on that occasion is already way past Earth, way past Earth. So, but it was Carl Sagan. We were on this stage together, and I was introducing him to the audience. It was a SETI conference. You may have even been here. It was a long time ago. Philip Morrison was here, Frank Drake, everyone was here. It was a long time ago. But I had the task, and I was a very young researcher here at the Science Center, very excited, and I had the task of introducing Carl Sagan, and I was kind of building up my introduction to a crescendo. I talked, because I wanted to get what was the essence of what made him Carl and what made him so inspiring to us. So, I talked about he was a scientist, an author, a television personality, but most of all, and I was trying to get, at the heart of what he represented, most of all, he's a curious fellow. By which I meant, he's curious about the universe. But it came out like, he's a curious fellow. So everyone burst into laughter, and very graciously, Dr. Sagan said, it's okay. And he went on with his talk. But that's going to bring me to my first question, which is, because you were also a curious scientist of the sense that, the universe is full of questions. I know many of us have asked or looked up at the stars. We've wondered that question about, are we alone? What's out there? I want to know from your perspective as a scientist, because there's so many questions you could pursue in a scientific career, what made this the appropriate question for you? What made this your question?
Well, I grew up with the first generation of television, so Flash Gordon on Saturday mornings. And so I think from a very early age, my worldview was simply that those stars were other people's suns, right? And there would be creatures that would see our star, the sun, in their sky. And so with that worldview, I never thought about this very much. It was just in the background. And then, getting an engineering degree and finishing a PhD in astrophysics, a very fortunate accident happened. As my first year in graduate school, I learned how to program, and this will date anybody in the audience who understands what this is, a PDP-8/S computer. First time we ever had a computer on our desktop. Now, it took me and my office mate, both of us, to get it on our desk, right? It wasn't tiny. But it was a miracle, and it had no language. You had to program it in Octal. I did this. It was great fun. Years later, I'm still a graduate student, and that piece of surplus equipment was given to an astronomer who had a brilliant idea about how to piggyback on the observations being made at UC Berkeley's radio astronomy telescope. So we could take a copy of the signal, and it could be analyzed to look for engineered signals rather than whatever the astronomers were looking for. But the guy who was given this piece of equipment looked at it and he said, "What do I do with this?" And they said, "Jill, she's still here. She used to do this." And he came and he recruited me. And I was so astonished. I thought, well, look, for millennia, we've asked the priests and the philosophers, anyone we thought was wise, what should we believe about life out there? And we got back some answer that was somebody's belief system. But now, suddenly, I was being presented the opportunity in the middle of the 20th century with some tools and some telescopes and the ability for scientists and engineers to do observations, to make experiments, to explore rather than have to believe. And wow, that's what hooked me. And I've stayed hooked. I think it's an amazing opportunity to try and answer a question that humans have been asking as long as they've been asking questions.
Because you had the tools. The tools are finally coming
there.
online. So you talked about some of those tools, about some of the projects that are underway and that are coming, also the Allen Array and so on. I'm hoping you can clarify for us now. If a signal arrives at Earth tonight, how likely is it that someone will hear? It's hard to know how much of the sky is being searched, how much searching is going on at this point.
Well, if it arrives tonight, the Allen telescope will be listening. But we only listen to 3 stars at a time. So if it's coming from over there, we'll miss it. That's why this laser SETI, looking at all the sky all the time, is so important. And we've known this for decades, but we haven't had the compute technology to make it happen. We still can't do it in the radio, but because the optical involves some analog technologies that we can use, we can get the job there. So I'm really excited about this new way of looking at the sky and wondering what else we'll find. So we're looking tonight. UC Berkeley is looking for 15% of the time in the northern and southern hemispheres. We could get lucky, but we could also miss it. And particularly if it doesn't last for a long time. So we do our signal processing in real time at the SETI Institute, but it means that the signal has to persist for minutes. Other places they record their data and process it later, and then if something is interesting, they go back and look, which means the signal has to persist for a long time. If it's transient, we don't yet have much sensitivity. That's what's going to come in the future. All the sky, all the time, all frequencies.
Well, I'm glad we're talking about the tools because, as it happens at the Globe and Mail in the last couple of months now, I've been writing a lot about quantum technology. Canada's big in quantum tech, as you might know, University of Waterloo, also out in British Columbia. You know, there's a company, D-Wave, that is already marketing a quantum computer. And of course, artificial intelligence as well, machine learning. So I know that, as you've touched on, a big challenge in SETI is just the sheer, going through the data, just the machine challenge of going through all that. Do you anticipate these new technologies that are beginning to arrive? Artificial intelligence is kind of here. Quantum computing may be here soon. Could that be another revolution for SETI? How might it impact that?
Oh, well, I said 12 ounces out of the ocean, but I'm not discouraged because things are getting better all the time. Both of these factors are going to be in our future. Right now, we're trying to understand how we can get the machines with unsupervised learning to tell us about signals that are in the data that aren't the artifacts that we've already defined. Right? And so we held a hackathon in San Francisco this summer, a code challenge all summer long. We're going to try and take the best of the classifiers that came out of that, see if we can make them fast enough to move up our pipeline at the Allen Telescope Array. And it's still in the beginning, right? These tools will be getting so much better for many other reasons. We don't have to invent that technology. We just have to get smart enough to figure out how to use it. As for quantum computing, it's going to be when it gets cheap enough. We'll use it.
Excellent. So before we came on my way here this evening, I consulted with my advisors about what questions I should ask you. And my 7-year-old daughter, Nico, had a very straightforward question. And it's actually a good question for journalists as well. The question is basically, what happens when you hear the signal? What do you do? I think for those of us in the world who might anticipate some kind of news event or anticipate how this might be disseminated, it's an interesting question. What do you do when that signal turns up?
Yeah, well, we have a plan. Whether or not we get to execute on that plan or the information leaks out is another question. But so here's our plan. The first thing that we do is to try and get the first thing we do, and you might not want to tell your 7-year-old daughter this.
Okay. She's in the audience, so cover your...
Sorry. They got it right in context. You're going to go, holy shit. We've been working on this for so long, and it actually happens, right? So then you're going to worry about a deliberate hoax. Mm-hmm. Probably more so than the folks who work on gravitational waves or other discovery kind of things. Because we have undergraduates at Caltech and here in Canada, there's really smart young folks who might think it's a giggle to fool us. So you're going to want to get an independent confirmation with hardware we didn't build, software we didn't write. All right? Get that. We've got the template for the paper. We fill in the blanks. We send the paper off. There's also an astronomical telegram system, right? Which is an email that goes to all of the world's observatories that subscribe. And we want to tell them because they've got all kinds of different instrumentation. And they can begin looking at what might be a time-critical situation. We don't know how long the signal's going to be around. They can begin looking to see what else might be there. And at the same time, we're sending them the discovery information. So that when we pull the next trigger, and that's hold a press conference, tell the world, mm-hmm. and the world's media can't get to the discovery team and say, tell me about it, what is it, what does this mean, right? We will have hopefully pre-educated a whole bunch of astronomers around the world that can work with their local media to interpret the reality of this. Because it's going to be sensational, and we don't want the media to have to make up their own stories. That happens already enough today. I'm sorry. So that's our plan. Mm-hmm. But that means that we keep this all under wraps for some amount of time.
That's going to be hard.
We knew about gravitational waves before the detection was
Sure.
announced, right?
Sure.
Embargoes are broken in it. So we have a plan. That's what we're going to try and do. That would be the best of all possible worlds because it would allow us to do things that are rational. We're probably going to end up reacting to the world's inquiries when it leaks.
Do you have time for a couple more? So, there was this moment when radio technology first arrived where, and Philip Morrison pointed this out in that Nature paper in 1959, where, by turning on the receiver, the signals might just be out there waiting. If you build a radio today and you turn it on, voila, signals from all over the place. So I know there was a moment where the world's astronomers realized, gosh, if we just start listening, the galaxy might be full of signals. It hasn't quite turned out that way.
No, it hasn't.
And I wonder what you think the universe is telling us.
I think that Phil Morrison didn't do the calculation to actually appreciate the incredible size of this cosmic ocean that we're trying to explore. And the other thing, because we've hardly begun to search, right? It seems like we've been searching forever, but we really haven't explored much. So the other thing that the universe might be telling us is, what's this electromagnetic radiation stuff? It's zeta rays, right? Obvious, it's zeta rays. Well, we haven't discovered zeta rays yet, right? But they may be in our future. So,
although there's that counter-argument that wouldn't a civilization use what is most accessible?
Could be. It's an interesting psychology. But there may be technology that we haven't yet invented, science that we don't yet know. And we just say, we got to stick around long enough to get smart enough to figure it out and then begin to use that. So, for example, I wouldn't argue that SETI should be funded at a huge amount, because we can't promise success. I mean, the astrobiologists looking for biosignatures, they can't promise success either. They're not really quite sure what the right biosignature is, but people have, certainly if we find a second genesis of life in this solar system, we know it's ubiquitous. All right, so it's a good bet, and you can begin trying to build instruments to look for these biosignatures, even if you're not quite sure they're there. But I think SETI is less certain that we know the right thing to do. So it's a kind of it's an endeavor that should be a long-term exploration. So we should do the best we can with what we have and keep going for probably a long time. And that's the hard part.
Do you have any sense of disappointment that may be a long time?
That's hard. If I got out of bed every morning and said, I'm going to get a signal today. All right? I'm probably going to go to bed disappointed. But I don't. I get out of bed, and what I'm trying to figure out is how to do it better. What can we do today that we couldn't do yesterday? And what can we do next week that will be even better? And then try and make that happen. And so that's my particular reward. And now that I'm so ancient, I've sort of taken up a new holy grail or hobby horse. I want to figure out how to get this exploratory science funded stably for the long term. So we need the equivalent of the university's endowment. It's very hard to raise. We don't have a lot of alumni. Right? But there's got to be something out there that will allow SETI to be funded at a modest level as a long-term endeavor. I mean, it took 25 years to find the Higgs boson and many, many billions of dollars. SETI may be longer term than that. I think we have to figure out how to keep going.
So the message to the youth, we need future scientists, but also future billionaires for this
No, I'll
endeavor.
take the billionaires today
right.
so that I can invest the interest
good
for
response.
those future scientists.
Okay, one last. I know people here, I'm sure, have many questions, so I'd love to turn it to the audience. We have a great audience tonight. I have one more question for you. This is a science talk, of course, so I'm not going to ask you what you believe is out there waiting for us. I want to ask you what you hypothesize is out there. What does your scientific instinct tell you?
We're looking for evidence of technology. So far, the technologies we've defined require transmitters of scale. They're not microscopic. Therefore, I think that whatever or whoever is building the transmitters are not tiny, unless it's some amazingly large collective brain. Beyond that, I don't care. Little green men, big blue women. I'll take anything. I'm interested in we're looking for the technology. We call it the search for extraterrestrial intelligence, but that's not right. We're actually searching for technology, and that's our proxy for intelligence. And anybody that can build and operate some kind of transmitter that we can detect, that's what we're looking for. And I'm just eager to see what nature can do, being far more imaginative than I am.
I think that's a great sentiment. And speaking of kind of, seeing what nature gives us, we've got the audience out here. I know human nature is at work. Everyone is full of curiosity, and I'm sure there are many questions. I think we have some microphones, we've got two people with microphones, two people in white lab coats, two hosts at the Ontario Science Centre, ready to, if you've got a question for Dr. Tarter, I guess raise your hand. Okay, lots. So I guess why don't we start right now? There's a microphone there for you, sir.
To follow up on your question about hypothesizing what kind of life would be out there, there are different schools of evolutionary thought in terms of how the evolutionary patterns would be. One school of evolutionary thought is that evolution proceeds in punctuated jumps. So it's all about historical contingencies that determine what patterns stochastically arise. So, for instance, if we were to run back evolution billions of years and we run it back until the present time, there's a less than 1 in a million chance that the same complex life that we know of as today will develop. And then there's also the school of thought that if you look at the evolutionary record, there's lots of lineages that seem to have independently and convergently evolved in the same way. So I wonder, what do you think? Do you think that because one of Isaac Newton's major insights was that the laws of physics could be generalized to the celestial phenomena? Do you think that the laws of evolution and biology could be generalized such that the same patterns would develop somewhere else, taking into account the stochastic processes that shape arisings of different?
Well, we now seem to understand at the molecular level the drivers for evolution. We begin to understand how that can work. I think that Darwinian evolution is likely to be a law of nature, of the universe, just as the laws of chemistry and physics, because that's what this molecular structure and the evolution we see coming, the emergent complex properties that we see coming out of that. It's just chemistry and physics. I think we'll see that replicated. That doesn't mean that anywhere, well, of course, in an infinite universe, there will be an infinite number of humans exactly like us. But in a large universe, you'll not probably see a human, but you'll see something that can generate a technology. And in fact, it may be not the technologists that we detect, but their machine offspring that we end up detecting. Anyway, I think Darwinian evolution's a good bet.
How about another question on that side?
Good evening. My name is Tony, and my question is, what do you think of the hypothesis that the intelligence that we're seeking can only be found in another dimension? And if this were to be true, would we not be better off throwing the billions at achieving that first in the end of the call?
All right. Well, first of all, I wish we were throwing billions at SETI. That's off by 3 orders
Just to
of
clarify.
magnitude, right? In terms of the fact that intelligence or what we're seeking may be in another dimension, that's in the realm of physics that we don't yet know. And I'm all in favor of funding basic research, curiosity-driven research in all different directions. And I don't think it's SETI that's going to drive that discovery. It's going to be our general exploration of our physical universe. And so, if indeed we learn, I mean, the cosmologists are telling us, right, that there are all of these hidden dimensions in string theory that are too small for us to see. I have a hard time wrapping my head around that. But if those turn out to be reality, yes. I was once bold enough to suggest that maybe dark energy has something to do with extraterrestrial technology.
How did that go?
It got Ray Kurzweil while really interested for a little while. It's an idea he hadn't thought of. So I don't know.
But I guess the strategy, I guess the point is the possibilities are endless. So why not look in the area where we're most familiar? That's what we can do. What we can do. Yeah.
Yeah, wonderful talk, Jill. Thank you. I noticed in one of the slides that there were various SETI projects throughout the world. Do they all work together, or are they all independent? And can anybody use the word SETI? And how are they funded? Are they funded differently or separately?
Well, they're all independent, and SETI is like physics. It's a discipline. SETI Institute is a particular group, an entity. For more than 50 years, we have had a committee in the International Academy of Astronautics on SETI. And that is where we have met. In fact, during the Cold War, it was the only place we could ever talk with our Soviet colleagues. Okay? And so there has been that scientific body, academy, that allows us to talk, to try and set standards. Right now we're actually trying to revise something that we published in 2000 called the Rio scale. And it's a way of quantifying, like the Richter scale for earthquakes or the Torino scale for near-Earth object impacts. It's a way of trying to quantify the veracity, the reality, the credibility of a announced detection and the significance or importance or potential impact of a particular type of announcement. And so it's within this academy that we're trying to do this exercise. And actually, they're meeting right now, today, in Adelaide, the International Academy of Astronautics Permanent Committee, Standing Committee on SETI. So how are they funded? However they can be. Right? There's no real federal funding for any project.
Was that the meeting where last year something came out that someone suggested they might have seen something?
Certainly did.
Yes.
Yes, there was.
Everyone's heart skipped a beat for a second.
Not me, I just got mad. Sorry. I'm sorry. Had we had the Rio scale then, it would have had a big fat 0. I mean, we did have the Rio scale. But
maybe you could just fill us in on what happened.
All right, so there's a great old telescope in the Soviet Union called the Rattan 600. It was configured to do a transit survey. So various panels of the telescope were tilted to different declinations, and they watched a number of sources go through their beam. Just one source was observed for a few seconds, at higher frequencies, and it was observed, I believe it was 39 times total, and once they saw a signal that looked like what a point source at a far distance would look like going through the beam of the telescope. It was never repeated. They couldn't ever verify it, and therefore I didn't get excited, right? Because if it isn't, I'm sorry, I'm hard-nosed. I spent my entire career not trying not to have any more wow signals. Right? Mm-hmm. People know what that is. So it was never re-observed. It was never validated in any way. It's an interesting thing. If you do Poisson statistics for the number of observations you're making and that kind of thing, you're going to get that.
Well, with social media, that just
of course.
Like that,
that's
yeah.
why that's one of the reasons. There was a year that we detected ET many times, starting with the really, really interesting WTF star. Where's the flux? Sorry, that was the title of the paper, right? And yeah, it's a real enigma, and it was suggested that it might be a huge megastructure under construction. We looked at it, a number of different radio telescopes and optical telescopes looked at it. It's still a mystery. It's one of these great scientific mysteries, and yeah, a couple of years in, and we're still not clear on what it is.
Of course, the discovery of the first pulsar in the 60s, that it crossed their mind for a moment, this regular pulse, that they might be seeing something.
LGM.
Yeah.
It was fine. LGM1, LGM2, LGM3. I'm not so sure there are that many little green men out there all broadcasting in the same way.
Another question. Here we go.
My name is Sean, and my question is, aside from our efforts to capture a signal that's extraterrestrial, are we making any particular efforts to transmit that word ourselves?
Good question.
Okay. So the argument often goes, if everybody's listening and nobody's transmitting, it's not going to work really well.
That would never happen in my house. Just putting that out there.
So you brought your daughter. You're responsible. Okay, so the fact is we're leaking all the time. We have a lot of technologies that emit radio waves and other optical signals. So we're not hidden, and we haven't been for 70 years. So if anybody is within 70 light years, actually 35, and have detected our leakage radiation, they may be transponding it back, and they may be the first, a la the signal from Vega, may be the first indication we have. But in terms of deliberately transmitting, okay, think about what you're suggesting. Okay, I have funding. I'm going to transmit for a year. That signal is going to go past any potential receiver in a year. They're going to have to be looking at you in exactly the right way, at exactly the right time to get your signal. And then it may not repeat. And, is this a wow signal? Is it the Rattan 600 signal? So transmission not only is more expensive than listening, but it is something that has to be undertaken as a very long-term project. It's not a 2-year plan, it's a 10,000-year plan. And we're not yet grown up enough to do that. Right? We are not yet stable enough technological civilization to undertake those long-term kinds of projects. So I say, yes, we should transmit when we grow up. So transmission's in our future, because I don't think it does any good to transmit for a short time. If that's my personal opinion. And it's a big debate within the community.
And in case people coming in tonight thought that was the transmitter, that's not.
We'll turn it on and put your hand on
exactly.
it, right? And then we'll see.
Yes, my name's Scott. Dr. Tarter, thank you for your interest in SETI and your passion. In order to convince supporters, you would want to convince them that there is a chance to find technological signals, and you have been concentrating on finding that note in a bottle. You're looking for a discrete signal. Ivan, in his introduction, mentioned Frank Drake, and I think it's the same Drake. In the 60s, he proposed a formula for calculating the possibility of intelligent life in perhaps a galaxy by assigning probabilities to different factors that would cause would be significant for an intelligent civilization. Have you ever experimented or thought about making that calculation? I know there are a lot of planets, more planets than there used to be or thought to be, and perhaps that would be a constructive exercise for you. Have you given that any thought?
Well, the Drake equation that you're referring to is actually not an equation that you can calculate anything from. It is, in fact, a wonderful way to organize our ignorance. But for those of you who have never seen the Drake equation, it says, well, let's estimate the number of communicating civilizations out there in our galaxy by taking the rate of star formation in the galaxy, multiplying that by the fraction of stars that have planets, tell me how many Earth-like planets there are in any planetary system. Now, what's the fraction of those planets where life develops? What fraction of life forms develop intelligence? What fraction of intelligence develops a civilization and technology? And lastly, how long is that technology used? Well, you're right. At the beginning of the equation, those astronomical terms, we're getting a really good handle on those. But the fraction of planets that have life, we haven't a clue yet. What's the fraction of life forms that life starts that provide intelligence? There have been a couple of papers this summer by two groups from Oxford. They tell me that the error bars on that factor alone are 10 to the 120, plus or minus 120. I mean, it's essentially, we don't know. And as bad as that is, the one that we really don't know is longevity. How long does a technological civilization last? Now, if you want to be generous and you're used to throwing around big numbers like astronomers, you can say that to within astronomical accuracy, many factors of 10, that n is approximately equal to L. That longevity, that, we can bound with 100 years, but we have a lower bound, but we have no idea what the upper bound is. 5 billion years more for the lifetime of our sun if we can't figure out how to move out of here. If it's life around a red dwarf, well, those stars, there's never been a red dwarf that's yet died in the history of the galaxy. So that's longer. But we just don't know. And so my approach to the Drake equation is to say n is approximately equal to L. If we detect someone else, L is large, because there are a lot of them out there. So it's a great tool for discussing possibilities and probabilities, but not something yet with which we have enough knowledge to use for any kind of precision calculation.
Two more questions. I'm going to suppress all the follow-ups I have to that.
Oh, you mean you could make it clear what I was trying to say?
Well,
You're not going to?
so one thing, a civilization that was around long enough, presumably could target every star with a mechanical device that would go out and look for planets. And so is it curious that we haven't seen any machines like that show up?
How big's the machine?
Good point.
You know, we grew up with Boldly Going and Battleship Galactica, right? Big wet biology out there. But maybe it's a Coke can full of artificial intelligence. That's what is doing the exploration. And I'll tell you, we can't find big rocks, 150 meters in size, that have our name on it out there. That's how poorly we've explored even our local vicinity. So we sure would have missed a Coke can.
Yeah, especially if it wasn't programmed to announce itself. So
right.
I guess that's the... Okay, another...
No, actually, even if it was, because most of our searches would exclude something within the solar system.
Of course,
because
there
we're
it is.
Trying to say a point source moving at sidereal rate on
We
the
would
sky.
call it space junk,
Yeah.
in fact.
Yeah.
Interesting. That's a good story.
But that's about to change. We're hopefully going to change our observing protocol so we could find something coming through the solar system.
Oh, there's the story.
My name's Anita. Thank you so much for all of your insight and everything you shared with us tonight. My question is less technical. I wanted to ask you about your thoughts on some of the movies that have come out about, extraterrestrials, and how a lot of them kind of focus on war, and how, humankind, and especially a lot of our leaders, would focus on war if we get a signal, if there's contact. And I wanted to ask about your perspective on that.
Yeah, right. So there's space westerns, right? It's all about guns and weapons, and we're going to go get them. I think it's just a modern representation of our own internal demons. So we used to have angels and archangels and what was the devils, all this kind of thing. Those used to be our fears. And now we're projecting it, given that we're in modern technology, we're projecting those same fears, in the form of extraterrestrials who are belligerent, who we have to fight against, kind of thing. I think it says more about us than what might actually be out there.
It's interesting that Contact is a very positive film. In the mid-90s, which is kind of an interesting time, and then I was,
Well, remember the book was written in the 80s.
Right. So, but then the more recent movie,
Arrival.
Arrival. No, but I'm thinking of the other one, the where they go to the black hole.
Interstellar.
It was pretty grim, and reflecting the state of our world. So right. I think that's
actually. Has anybody who's seen both movies, did you catch the fact that Matthew McConaughey did exactly the same scene in both movies as he explains the twin paradox? If you go out and travel near the speed of light, when you come back, everybody that you knew and loved will be there. So exactly the same scene in two movies. I wonder how often that happens to an actor.
Or he's going to be typecast as explaining
the
twin paradox.
Right? Time dilation.
Okay, one last question. Here we go.
Hello, my name is Edgar. Thank you for the conference and all your work. My question is about this book that came out like a few years ago, science fiction, The Three Body Problem, where 6 new Chinese authors say that maybe there is a possibility that the universe is a black forest where all the civilizations are hiding themselves because the universe, they're fighting for the resources, and then they are afraid of being destructive somehow. So is it like what are your thoughts about it, first of all? Or if we are looking now for signals that are like specific messages for us to, like, hey, we are here, in that case, we are not going to receive those signals. The only possibility for us is to receive signals like noise signals, like the signals we are emitting now from Earth. So I don't know.
I'm so glad you asked that question. The question is, what if no one wants to talk to us?
Then maybe there's a good reason in the sense that if I were an advanced technology, I might not want to talk to us either in the condition that we're in, right? So I wasn't quite sure whether you were talking about the Chinese science fiction novel, The Three-Body Problem, or whether you were talking about the kind of thing that Stephen Hawking has brought up about maybe we shouldn't transmit because, they'll come, and remember, it didn't turn out really well for the natives when Columbus showed up, right? And so The Three-Body Problem is a science fiction novel. It gives me the creeps, and I would never have done what she did, which was to transmit, without a global consensus that this is what we should do, right? But in terms of the Stephen Hawking situation, look, he's supposed, first of all, he's brilliant, right? So it's kind of difficult to disagree with him. But nobody's an expert in this field, all right? So he's proposing they're going to come here and therefore pose a threat. What does that mean? If they can get here, first of all, they're going to write the rule book, but if they can get here, they are older and technologically far more advanced than we are. I wonder if it's possible to get to be an old, advanced technological civilization without outgrowing the aggressive tendencies that probably helped you to become intelligent in the first place. And so I think about Steven Pinker's book, Better Angels of Our Nature, and where he claims that we are today kinder and gentler than we have ever been before on this planet, and that is a feature of cultural evolution which is likely and perhaps even necessarily going to continue if we are to have a long future. So, if you weed out the aggressive SOBs as you get to be an older, sustainable civilization, maybe we don't have anything to worry about should they come here.
So pick your Stevens carefully. In this case, Pinker over Hawking.
There you go.
So, Jill Tarter, thank you very much. What a wonderful, really enjoyed that.
Thanks, guys.
Thank you, Jill. Before I thank Jill and present her with the honorarium, by the way, I should introduce myself. I'm Charles Darrow, past president of the Toronto Centre, and it's good to be back here.
Yay!
When I used to chair meetings here, I always started them out, and I always used to say, if anyone wants to look very good at public speaking, just follow me to the lectern. Right? So before I thank Jill, I really have to thank my wife, Sarah, for honoring me and for thinking about this lecture series. And as Dennis mentioned to me, I'm having a bit of a Schrödinger cat experience right now because I'm honored, I'm embarrassed, and I'm humbled. And I'm a very humble person, and this is not me, but this is really more for everyone here. Walking the dog the other day, there's a lot of interesting people where I live outside of Boston. The movie Spinal Tap, they say that Boston isn't a big college town. Don't worry about canceling the show there, but apparently it is. Tufts and Boston University, MIT, and Harvard. And one gentleman I ran into walking his dog is a scientist, a medical doctor, and he distilled it down to me, and he said that everything that we have around us, this technology, anything that's not natural, even if it's natural, has been modified. It's because we've been curious. And I really want to thank everyone in the audience today for coming here because obviously you're curious. You want to learn a little bit more about the universe. And I also want to thank Jill for being curious and sharing her results of her curiosity. So before I also present Jill as the honorarium, I thought I should like to give her a little bit of a gift, reminder of Canada, and I want to get something a little bit different than the standard maple walnut ice cream or Smarties or toque or hockey puck or maple syrup. And I thought, what could be unique and different? And I remembered the Royal Canadian Mint last year had a special series of coins that were honoring science. And there was one actually with the Dominion Radio Observatory on it. So I thought that would be a nice reminder of Jill's visit to Canada. And so on behalf of the Royal Astronomical Society of Canada and the Ontario Science Centre, I'd like to thank you kindly for coming and sharing your knowledge with us today.
Oh, thank you.
Thank you, Jill.
He told me it glows in the dark.
The little radio signal there, the sine wave, that really works.
Oh, fantastic! It does. Oh, this is super, and you need to keep this as a tradition going into the future.
I think I got the last one from the Mint, so so
you got even more precious.
Okay. Thank you very much.
And you should remember that Laurent Trottier goes to his own lecture series. So you should continue in that for the Darrow lecture.
Thank you, Jill.
Well, it's been a great evening tonight. I'd like to thank Jill for that very stimulating talk and the discussion with Ivan. I'd also like to thank Ivan for his contribution for the evening, asking the questions in the conversation. Thank you very much. And thank you all for joining us this evening. The next talk in this series will be on October 26th, and we'll have another great conversation here with former NASA astronaut Scott Kelly. He'll provide a unique perspective on both the challenges of living in microgravity environment and the opportunities for future human space missions in a time when we are asking ourselves whether man can really live beyond Earth orbit. The moderator for the event will be former Canadian astronaut Dr. David Williams, and he and Kelly will sit down for an in-conversation event, Astronaut to Astronaut. Rounding out the series is American physiologist David Julius on December the 4th, so I hope that you will plan to attend some of these talks. Thank you again for joining us this evening. The ushers will show you the way out of the building, and you'll be going up to the upper level exit. RASC members are invited to remain in your seats for our weekly meeting announcements. Okay, thank you very much for coming tonight. Good night.